members of Electronics class Tanzania. Our coach, Engineer Mhina, is about to coach you today about transistors. We are in lesson 4. Also in lesson 3, we started the basics of transistors, and today also in lesson 4, we'll continue about transistors. Transistors is a semiconductor device which during invention of it has bring a lot of changes in the electronics industry. Before transistors, we are using vacuum tubes, but were replaced by transistors due to the many advantages of transistors. Some of the most advantages of transistors is they are small in size, they are light in weight, rugged, and also transistors are using small power and consume less voltage. Transistor is a semiconductor device and is made up of two types of materials, which is P and N materials. The material normally used to make a transistor is silicon, but also Gemini material is used, but popularly silicon is mostly used. The silicon material is being doped with P impurities to make a PN device. Also, N part is doped by N impurities to make N materials. And a transistor is like two diodes being connected back to back. And we have two junctions in transistors. There is a emitter junction between a emitter and a base, and there is a collector junction between a base and a collector. So we have two junctions. The transistor has current. We have a base current, we have collector current, we have emitter current. The transistor has mostly there are two applications in the transistor. Transistor is used as an electronic switch. This is a very fast switch. And also transistor is used as an amplifier. We amplify small signal to much larger signal. In computers, there are millions of transistors there. Even in our smartphone, we have some millions of transistors inside there. So a transistor bring a tremendous change in electronics world. Now we'll see how in mathematical form how transistor is used as a switch. Also, transistor can be used as an inverter, which a small signal you find a big signal, or a big signal you find a small signal. So in today's lesson we'll see in a mathematical form and electrical representation of a circuit as a switch, also as an inverter. There are two types of transistors: the bipolar junction transistors and unipolar junction transistors. Why we say bipolar junction transistors? It's called bipolar junction transistors because there are two carriers, electrons and holes. Both are flowing. But in unipolar junction transistors are called FET or field effect transistors, which only either electrons or holes which are carriers. But in bipolar junction transistors, which are popular, and today also we'll learn on bipolar junction transistor as a switch and a bipolar junction transistor as an inverter. And this bipolar because the holes and the electrons are carriers, are all flowing as carriers. Bipolar bipolar junction transistor. We have seen we have two types of transistors, the bipolar junction ones and the FET, the field effective transistors. And these are called bipolar junction transistor because they have both carriers, holes and electrons. We'll see electrical representation of these bipolar junction transistors. In bipolar junction transistors, we have two types. We have NPN, and we have PNP. In NPN, we have P material as base, and the base width is small in construction. The base width is small. We have P here, we have N here, also we have N here. This is emitter. Here we have base, IB, and here we have collector, IC. In a transistor construction, collector is much larger compared to emitter and the base. The base width is small. Also, the N, which is on emitter side, is heavily doped, but the collector is less doped and the base is intermediate between emitter and the collector. A transistor has current. Let's say transistor current. Transistor current. Transistor currents are emitter current, base current, collector current. This here, transistor current. Also, electrical representation of a transistor NPN can be represented this way. We have our cycle there. Electrical representation of NPN transistor. We have our IB here, our base. We have our emitter current here. Also, we have our collector current here. We want to see the voltage representation of a transistor NPN. So here is our base, here is our emitter, here is our collector. So we have voltage between base and emitter, VBE. We have voltage between collector and emitter, V. Collector and emitter, VCE. This is C and E. This is E. Also, we have voltage between base and collector, V, B, C. So these are transistor voltage. But also we have PNP. PNP, I will show here, PNP. PNP, as usual, base is small. P here material, N here material, and P again here. This is our emitter. This is our base. This is our base. This is our IC, our collector. In the electrical representation of PNP, we have our cycle here, in PNP, the arrow points towards transistor. Here our collector, here our base, here our emitter. So how can you differentiate between NPN and PNP is by looking the arrow. If the arrow points outward, the arrow point outward the transistor, this is NPN transistor. But if the arrow points toward the transistor, this is PNP transistor. In transistor, when the arrow points towards conventional current is positive. When the arrow points toward the transistor, the conventional current is positive. So here, IE is positive. But IC will be negative and IB will be negative. Here, in NPN, the arrow points outward. The IE will be negative, but the IC will be positive and IB will be positive. Conventionally, in a transistor, when the arrow points outward, the conventional current for that current, IE, is negative. But if the arrow points towards the transistor, conventional current at IE is positive. In other words, I'll put here. In other words, by using Kirchhoff's law in a transistor, also I can show you here in transistor by Kirchhoff's law, IE plus IB plus IC is equal to 0. Bipolar junction transistor, in short, is BJT, bipolar junction transistor, as a switch. Why we say as a switch is because a small current control high current. We apply a very small current in order to control high current. Let's see a circuit of a transistor as a switch. Let's have our source here, a 6-volt battery source, and here we'll have our switch. Let's say S1 switch, and here we'll have our current limiting base resistor. This is our transistor here. This is an NPN transistor. The arrow points outward, and here we have our diode, LED, light emitting diode. Here we have our resistor here, and we have our closed loop circuit. This is R1. Let's say this is R1, this is R2, and we control a motor. Then we have our motor here, and this is our NPN transistor, because the arrow is pointing outward. Why we say is a switch? When we apply a small current here, then the large current will flow from collector side to emitter side. So if here is 6 volts, then this point will be 6 volt here. This is our switch. The the base emitter voltage, in order the transistor to allow the current to flow, we need VBE, we need 0.6 volts. In transistors, the current gain, or the beta, is between 100 to 300. This is the factors. In our calculation here, we'll use beta as 200. The beta, or current gain, is equal to IC over IB. So if you have a beta, you can have IC. So IC here is equal to beta times IB. So we can find IB in this circuit. IB, our base current here is IB. We flow this way. Let's see, find IB. Our resistor here, let's say, is 500K. And here we have 1K kilo ohm, this kilo ohm resistors. By using Ohm's law is equal to voltage IR. Ohm's law, voltage is equal current times resistance. So if we want to know the current, is equal to voltage over resistance. So here, if we want to know the current here, we have to know the voltage across the resistor. So if if this point is 6 volt, also we close the switch, then here we have 60 volts here also. And here the voltage is 0.6. So the voltage drop across the resistor will be the difference between this potential to this potential. So is 6, the voltage drop in the resistor will be 6 volts minus 0.6, the drop here, over resistor, which is 500K. And here we have 5.4 over 500K, which will be equal to 0.108 milliampere, because we divide by kilo ohms. So this is our IB. So to know our IC will be equal to 0.108 milliampere times beta, which is 200. Then we have our IC 2.16 milliampere. So our IC here is 2.16 milliamps. This is the IC current. So we want to know how much voltage will be here. That's our aim, the voltage which will control the motor. We have applied a small current, which is 0.108 milliampere. That's our IB current. So we want to know the output voltage to control the motor will be how much. So in this circuit is a switch. Here also we have 6 volts here. This point we have 6 volt here. So we want to know the drop here, the drop there at R2 resistor. We have, if we want to know the drop here, we have R we have, because we know the voltage is equal to IR. We have current, which is 2.16 milliampere. We have a resistor, which is 1K. This is kilo ohm, 1 kilo ohm. So here we have a voltage which is 2.16 volts. 2.16 volt will drop here. And so, if we want to know the voltage here at this point, the diode, normally the diode drop is the diode drop is 2.2 volt. This is the diode drop. So to have the voltage at this point, we'll subtract with high potential, the current flow from high potential this direction, current flow this direction, from high potential to low potential. So 6 minus 2.16 will have 3.84. We have 3.84 volts, which will be here. 3.84 volts will be here. Also, there is a dropout diode, 3.84 minus dropout the diode, which is 2.2. We'll have 6.4 volts, which will be here at this point, this VC. So VCE will be equal to 1.6 volts, 64 volts, which will be controlling the motor. So we have seen transistor as a switch, a very small current, 0.108 milliampere, controls the voltage to the motor, and we have 1.64 volts voltage in order to control our motor. So here the application of a transistor, our BJT NPN transistor, acts as a switch. A small, very small current control large voltage into the motor, and our motor can work according to our what we want. So it's just a matter now to vary the parameters. You can vary the voltage, you can vary the resistor in order to get what you want at the output of the voltage emitter, VCE, in order to control what you want to control. For instance, here we control a motor, you can control a refrigerator, whatever apparatus you can control here, but you can vary these parameters and you can get what you want. Let's continue our class. Transistor as inverter. BJT is abbreviation of bipolar junction transistor. Here we'll see the function of a transistor, BJT bipolar transistor, NPN as an inverter. The electrical representation of the circuit as an inverter. Let's say here we have our base resistor. Here we have our transistor NPN. The arrow is pointing outward the transistor. And here we have our collector resistor. So let's say here we have our 9 volts positive, 9 volts, and here we have our paths of 5 volts, So this is I, IC, IE, and IB, our base current. Normally in NPN bipolar junction transistor, the beta is ranged from 100 to 300 beta. So let's see our transistor, a BJT, as an inverter. Let's have a chart here, V in and V out. V in and V out. So let's say we have a circuit of 50K. Let's say we have 50K here. Also you have 50K here. In a normal situation, because we just want a very small current to make the conduction between the VCE. We just need a very small current. That's why we put a large resistor. But if we put here a small resistor, let's say our this is R1, R2. Let's say R1 is 1K, from 50 to 1K. That means high current will flow. So if we have very high current, very high B, very IB current, base current, the transistor will go to the saturation mode. So in saturation mode, VCE will saturate, will be equal to 0. This is in saturation mode. Saturation mode. And we get saturation mode if we apply high current. Also high current will flow this way. Then the VCE will be 0. So our 5 volts here, we apply very small current, resistor, very small resistor, high current will flow, so we have V out 0. But if IB is 0, if IB is 0, base current is 0, there will also be nothing flowing in this here. Also IC will be 0. So if IC is 0, there will be no drop here. There will be no drop at R2. R2, no drop. No drop voltage. So 9 volts also will be appear here, 9 volts. Because here no drop, we have our 9 volts here. No drop, 9 volts will be here at VCE. So our VCE will be 9 volts. So at 0 voltage, output will be 9 volts. So you can see here our NPN to this configuration with these parameters act as an inverter. So we can put also another chart which can show also in this way. In this way, our V in here, our V out here. So you have high value, you get low value. You get low value, you get high value. So this is a representation of NPN as an inverter. Hi viewers of Electronics class Tanzania. We have seen lesson 4. We have learned about transistors. Also in lesson 5, we'll continue learning about transistors. Transistor is very wide, has much use in electronics, so we take a lot of time so that we can know and understand transistors. On today's lesson, lesson 4, we have seen transistors as a switch, transistors as an inverter, and also you've seen a bit of how it was made. An NPN transistor, PNP transistor. Also you've seen a bipolar junction transistor. What does it mean? Also you've seen unipolar transistors or FET, field effect transistors. What does it mean? Thank you for watching, and don't forget to subscribe, like and share, so many can enjoy electronics class Tanzania. Thank you. See you in lesson 5.